Okay, let us start with the today's. So today is I think it's day 19. I shall check it one later. So last day what we have learned, if I remember, the uh, discussion that you have a complex and you the complex is going to face a reaction. So once the complex faces a reaction, then what happens? So once the complex faces a reaction, what happens? Either there will be an addition, I mean simply, either there will be an addition or there will be a substitution, or there may be any on one of the this ligand, because we are discussing about the transition metal complexes. So the addition, the subtraction, and whatever the substitution, we will discuss in terms of ligand, right? So metal is not going to substitute it. So we are think and largely we are interested about the ligand substitution reaction. So when we are discussing about the ligand substitution reaction, what we did on the last day, we have seen that there could be different pathways. It may happen that during the ligand substitution, the leaving group is going first, I mean dissociated first from the uh, parent this complex, and then the entering group is uh, attached to the complex. Or it may happen that in the presence of that leaving group, the entering group associates with the complex, and then the leaving group goes out of the system. So depending on that, we have shown, it can be shown that there are three types of mechanism. One is dissociative, second is associative, and we kept another, it is interchange. And why? I mean, if we just go through this, we have seen that the interchange mechanism is somewhat is closely related with the associative mechanism, but there are a little bit differences, because in associative mechanism you could trap the transition state, and you could characterize it. You can feel the presence of the transition this state. But in interchange mechanism, the association happens, but it is so fast, is so less. Uh, uh, I mean, the timeline is the time frame is so less that you cannot uh, trap or characterize that transition state. But as I told you last day also, again I am repeating that with the advancement of the spectroscopic tool, it can be found that this interchange mechanism also you can feel the presence of the transition state by a very fast. I mean, the spectroscopy, as you can understand, this picosecond and all these nanosecond, picosecond, and all these things. If you just think for 1 second, you can understand that why these terms are there, or why this spectroscopy is associated with some time frame for this spectroscopy. Because if a species is very short lived and even then with that I mean if it is more than this time scale, let's say a reaction is in the nanosecond region. I mean, an intermediate forms, associative intermediate forms, and that stays in the solution for nanosecond. So if you just want to measure it with with the instrument that can measure something that is present within the solution for 1 second in the seconds or I mean, second order means not two order, second order I mean time scale second order, t is a second, then you cannot and if the intermediate is nanosecond you cannot uh, measure this reaction. But if you have some instrument that can measure in nanosecond level, then you can you can find the feel the presence, or you can just detect the intermediate in the solution. Now, if you have something in the microsecond range, the lifetime is in the microsecond, then if you have an instrument in picosecond, you could easily measure it in the microsecond. So with the advancement of spectroscopy, this interchange and associative mechanism are quite merging because people could at least detect the this transition state. Now we have understood the mechanism. Now let us go to the real picture. So real picture. So this reaction mechanism for this, I mean for your standard, we will only deal with the square planar complexes and the octahedral complexes and different aspects of this mechanism in the square planar and octahedral complexes. So let us first, because square planar complexes, as you can understand that square planar complexes has what is the difference between? I mean, if I mean not in very just in layman's idea, if we just see the difference between the square planar and the octahedral complex. So what is the difference? That square planar has uh, less steric hindrance. So what do you expect then? So if you just imagine a square planar complex and just imagine a octahedral complex. So if we just see a square planar complex and if we just look at a octahedral complex, so what is the point? We can see that the very simply the octahedral complex is a little bit more crowded. So if it is crowded, then definitely it is expected that here for octahedral complex for this octahedral complex we can expect that maybe I mean association may happen, but dissociation is also is more likely. But here we expect that it is associative mechanism is operative. But there are some certain complexity, and we can see that it is not always like that. And even if it is associative mechanism, then also the rate of I mean the rate of the reaction may depend on the entering group, or it may not depend on the entering group. So these things we will just see what are the characteristics of ligand substitution reaction in this square planar complexes. So the first thing we will read is the ligand substitution in square planar complex. Okay, so let me first put a we have taken an example from the book only. I have taken all the examples today from book so that you can understand. Once you read, then we can go for more examples. So PTCl diene plus, right? And if you now this diene plus. Now this is the reaction. What we are doing, we are replacing chlorine with the iodine. Now what could be the possibilities? So number one possibilities is that the rate is dependent only on complex. So if the rate is dependent only on complex, then what would be the rate? Rate is equal to very simply Q1 into concentration. Okay, here you just look at this. When we write any complex, then we keep it in this, right? But here when we are giving the concentration, then you can use a second bracket, because we just do like so. These things you can do. So this is important. So please keep it in mind that here the third bracket actually uh, signifies the concentration, but as we are also accustomed with this writing a complex with a, with the third bracket, so here some uh, a little bit of things you should remember. So either you do write it in the that way, or you can just write the in plus things. But this is better. I mean, it is better for you to understand. Okay. Now the second thing is that it may happen that the rate of reaction depends on both I minus, both complex. The entering. These things is they are written how we do come to this K2Y, not Y, because we have taken I minus. Now, what happens? Yeah, plus. Right. Now the point is that how it is characterized. So now you see that just do not look at the rate equation, that you can deduce from the rate equation if you just do it in that way. Now the point is that the rate can be deduced from the concentration, like what is the concentration of these things. And if you cannot, you just let me know, I shall do it. I mean, it is there in the book also. So now what happens, how does it done in the laboratory? So if you see that now there is a I minus, now you have a option of increasing the concentration of I minus to a great extent, so that the I minus concentration practically remain the same. And if it practically remain the same, then again the concentration depends on this the complex concentration, and this is called, and you feel that it is not the second order, but it is pseudo first order reaction. And this is done, how it is done. So reaction is done with different concentrations, starting from very small concentration and then going to the high concentration. And then because of this I mean, so that it becomes easier for us to understand, so we do it in the pseudo first order reaction. Now there is the, if it is I minus, so we have chosen is that I minus. So does it uh, uh, remain the same if we take any other, let's say if I just make it Br minus, if you make it Br minus, or you can make it NO3 minus, or you can make it water or anything. So does it depend? So I am not explaining it to a great extent, because sometimes it becomes a little complicated, because now I just want to make the points, and if necessary I shall explain it. So here we say that the nucleophilicity factor that affects the ligand substitution. And how does substitution, and how does it substitution? So how does it measure? So you have a solvent. So you have a solvent and you have a CH3OC. Let's say methanol is the solvent. And then the nucleophilicity of methanol is taken as reference. So you have to mention the reference with what is the reference of your study, and then you can, let's say bromine nitride, anything H3PO4H minus, whatever you take, and then you can get the nucleophilicity of that particular case. But here the point is that, so you have the complex, let's say platinum Cl minus, right? You have the complex like this. Now, if I say that nucleophilicity of I minus is better, more than Br minus. So if I make the statement, so do you think that this is a true? So I'm writing this and I shall go back to the chat. So nucleophilicity of I minus is higher than Cl minus. So the first question is it is the comment right? Is the comment right? If it is right, then why? If it is wrong, then why? What is your support to this? I shall not go to the critical this uh, explanation right now, but just try to understand. So I think the question is clear. So what are, I mean, try to understand that if I say nucleophilicity, what does it mean, and how does it, whether the statement is correct or not. Quick. What happened? Is the statement correct that nucleophilicity of I minus is more than Cl minus? No answer. So please say something, yes or no. I mean, even if it is wrong, no problem. Let us discuss. It is not that I shall give any marks or anything. I just want to see that how do you see. I mean, as I always say, that whether you could read between the lines, or whether uh, how to see the problem. Yes, for polar solvent. So one answer. So any more answer? Okay. I expect two more answers, and then I shall discuss. Okay. So I can understand that. I mean, the reason why I kept that question, that really leaves. So what you people are looking for is that you are looking only this I minus and Cl minus, and your mindset now is in the organic chemistry mindset. So you are looking at something from the organic chemistry perspective, but here you try to understand that whom to join and whom to leave. I mean, if you are looking for a nucleophilicity, then with respect to what? With respect to the metal center. So it might happen that platinum is related to I minus. I mean, this statement is true for platinum in, let's say, polar solvent. Okay, fine. I mean, that is another factors, and after that. But it might happen that it is not true for, let's say, copper, right? So they are, and that wholly depends on the orbital matching. I mean, if you just look at this periodic table, you can see that there are 3D, 4D, 5D. So there are changes in the orbital sizes, and then the whatever the nucleophile, or whatever is for ligand substitution reaction, whatever is coming as nucleophile, that have some this orbital sizes, and all these factors actually uh, this contribute to this. So you cannot say that nucleophilicity of I minus as such. So what you need to see, that nucleophilicity with respect to. So actually it is written eta pt. So here this is the nucleophilicity. So every time you have to uh, this mention first the metal center that you are looking for, and then you have this term is log of K2Y and K2 0. 0 means solvent, right? And in that way there is another term. I shall not today complicate it. So there is a nucleophilicity, this discrimination factor. So if I mean if I want to generalize something, then how can I generalize that? That also could be done with this nucleophilic discrimination factors, right? So I mean, I think it is clear that you can understand that why this nucleophilicity is not universal. You cannot say like organic, because organic chemistry, the center is the carbon, and it is attaching to the carbon, it is going from the carbon. But here you have a plenty of metals, and all these metals again have different different charges, and different these orbitals and all these things. So it is a bit complicated. Now the most important part of the, okay, so yes, so the most important thing is that all of you are quite um, familiar with the term transitions, trans effect, right? So trans effect you all are very accustomed with. So how does, I mean, why this term actually arises, and how does this effect? So if you just look at the trans effect, so what we say in trans effect, oh, I am coming with the term. Let's say you have X, you have X, you have x. Okay, let's see. Let you have y and you have x. So let me, the living group is x. Let me take that living group is x. Now the point is that here this is one option and this is other option, right? So first the living group may leave the this x or this x. So which one will go? Which one will go first? So now the first is that so you should look at this problem, this trans effect. So if it happens that the so here we'll see that y trans effect wise y is greater than x, and here we will say that trans effect of x is greater than y, right? Now this problem you have to look to two sides. One is the ground state and second is the ground state mean when when the this complex is just this complex, and then the transition state, right? Now if I ask you, let me all of you know trans effect, so let me ask you from the bonding uh, uh, aspect, what is the effect in the ground state? Please try to think over it. I am giving you the hint. Look at the shape of the metal complex. Look at the or this this orbital. I mean the overlapping orbitals. That what y and x is sharing, what is x and x are sharing. So just we try to remember what happens in square planar complexes. If you cannot, you just remember that this octahedral complex you have z orbital, and then if you have xy orbital, then how does it placed, and then if it goes from this uh, z if goes out, then what are the orbitals that are placed? I mean, if you take this x and x and y, and then what are the orbitals? In that way, you tell me that how does this ground state influence in the trans effect? Okay. So if it is the sound you can give, so it will be, if I can unmute you, it is really good, but I cannot. So tell me, whatever you feel, even if it is wrong, no problem. Please feel free to interact. How does the ground state affect? See, try to understand. This is again the application of the this bonding, right? This not only I am teaching, I am trying to teach you something as reaction mechanism, but you have to correlate, and then it will be very easy. Don't go for Google or something. Whatever comes to your mind, please let me know. Whatever comes to your mind, you write. So how do you think? I mean, think of that your X and Y is sigma donor, then what is happening? Think in that way. How does ground state affect? So what are the orbitals that, let's say, Y and the trans X are sharing, or are the orbitals? What are the orbitals? Quickly write. So I'm not telling you no to have some idea. So Kundan, so you just think of it. What are the orbitals? You do you have, all of you have pen and paper with you? Let's think in the right. Yes. So you write. So what is the Z direction? An octahedral Z, and then X and Y. So what are the orbitals available in the XY direction that you write? Along Z axis, what is the orbital available? Along Z axis, the orbital available is dz2. What is the orbital available along XY axis? X and Y axis. Think of the T2G Eg. Why T2G Eg is higher energy? X2Y2. Fine. Dx2Y2. Now you tell me that if you see the remember the the square planar complex. So Y and these one, they are sharing the opposite phase of the same orbital. Yes or no? Let Yes. So if they occupy the opposite orbital of opposite phase of the same orbital, then if one of them is very good sigma donor, so it gives much electron to this, and then metal becomes saturated. Do you agree? And the bond trans to it weakens. So was it very difficult? Now you tell me. Was it very difficult? Yes. See, here I am writing. So how we see that? If we have x, this is x-axis, this is y-axis, this is z-axis, right? Now for this, what I wrote, this is M, This is, let's say, y. Here it is x. Here it is x. Here it is x, right? So I can change it because this is the axis. So we can write is a, it is b, it is b, it is b, right? Now you have the dx2y2 orbital in that way. Yeah, z orbital I am not drawing, right? So they are facing the opposite phase. Now, if A is sigma donor, strong sigma donor, then this bond, this is reluctant to take electron from this side, so this bond weakens. Now, if A is greater sigma donor, so this bond weakens. Now, if B is greater sigma donor, then this bond or this bond, anything. But for our better understand, this bond weakens. Here, both of them has the same effect because if I have both of them B, but then any one of it will break because both the bond are a little bit weakened, right? I mean, if I give a C, then it will be easier for you to understand at this stage that if C is greater than A, then this bond weakens. Then this will go, and if this goes, then this will go. If A is greater than C. Is it clear? Now is it clear, or again I have to explain? Okay, now I am giving you the clue that the transition state, this transition state uh, stability depends on the pi acceptor property. Now just think of it. And this is the point what I'm always telling you, that this is the point you should, once you see a problem, you start from the bonding, and these things you must keep in your mind, that what are the orbitals, and immediately you can tell. I mean, let me know one thing, that when I told you the answer, do you feel that it was not, you couldn't understand, or uh, you cannot do that, but you didn't think in that way, right? And also think of this. So if this is the ground state, now what happens in the transition state, and what could be the possibility of transition state that you think first? So what could be the transition state? One is that dissociative, another is associative, both are possible. And also in the transition state, I'm giving you the answer that the better pi acceptor plays a role, so that you now uh, try to answer. And ultimately, when trans series you see, then it is combined to with these two effects, because what will affect the series that you and the combined effect actually is reflected in the reaction. Okay, quick, what, and very simple answer. So what is happening when some ligand is coming? What is happening? The same way, this opposite face thing is again is working. Yes. So the pi acceptor, so very simple. So when some ligand is coming, it is bringing some electron density, and the metal needs to accept that electron density. And if the opposite one is a better pi acceptor, then the electron density from the metal is accepted in the pi orbital, and metal is remain a little bit. I mean, stress is a little bit less, and it will go to this opposite to this pi acceptor. This is very simple I mean the point. So like for pi acceptor, this is sigma luna, and this is pi acceptor. So can go to the, so transition state pi acceptor stabilizes the system and ligand prefer to bind to the trans of pi acceptor ligand. And these are called, as I told you, these spectator ligand, and they actually affect. And generally, this is a very common question. Like if you have, let's say, platinum NH3, so let me see the example. Okay, so platinum NH3 whole 4 2 plus, and you are changing with platinum Cl4. Now you tell me, just do it. And NH3. So what would be the, so let's say final product, if this is the final product, what is the geometry of these in these two cases? If I tell you that this is the series trans effect NH3 Cl1. Now tell me, what is the geometry of the end product? Write it in your copy, and then I shall go back to the chat box. If needed, please tell me. I can pin it here only. How can I pin it? The screen. What is the product geometry? No, no, square planar is fine. Trans or cis. Just drop TT NH3 whole 4 square planar. Yes, square planar state you write. Then you uh, 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 substitute with chlorine. With one chlorine product, then second chlorine, and one NH3 product, second NH3. Then what is the geometry? So it will be like this. The composition is same in both the cases. Am I clear? Okay, trans in case of, so other answers, let me know. So Kundan, can you explain? The first one is same for not same, but yes, same for, because one they are different compound. The first one and the second one, why it is trans? You are right. It is trans. So so let other people give answer, or they may uh, be ready to accept your answer. Let's see. Please draw and do, and you do it. You do it. Yes, CLA add to oppositely, then trans effect. Trans effect means in the first place it is not trans effect. Do it I mean properly. No, your answer is wrong. No, so answer is right. I mean, for PTCL4 you wrote run. Okay, fine, it's okay. So anybody else has any? I mean, agreed with Kundan, or you have any other options? That just let me know. So generally, this type of questions come in trans effect all over the net and all these things. So in some cases, and then the challenge is that if it is given that this, let's say, CL minus is greater than NH3, or it is not that you have to remember it, in that case you have to look for the orbital, like if it can give NH3 and PH3 like this, and then you have to see at the metal. I mean, how it could be complicated. I'm telling you that you have a metal, and then you have NH3 and PH3, let's say. So in that case, what you have to look for, that these metal, if it is a 3D metal, then whether it is compatible with the this P more or N more, and in that way you have to look. Which part, Anusha? First, some of you tell me whether you are agreed or not agreed with Kundan, and then I shall explain the all the total thing once more. Anusha cannot because she wants more explanation. So other people, okay, nobody is answering. So why other? I mean, only these three people are responding. The others are sleeping, or what happened? Okay, let me explain it once more. So the total point is, I'm writing it once more. The total point is what is the trans effect. So you please look for the this definition in the book that trans that transposition to the living you do influence the event substitution for square planar complexes. Now, one is that in ground state, number two in the transition state. So, how does it do? The transition ligand do share the or opposite lobes is better because always it is not opposite lobes of same orbital. So, 1, 5, ligand means yes, strong sigma donor intense the opposite bond. Okay. In transition state, incoming ligand. Don't look for any book with this language, okay? Because this is just to make you understand. Means electron density bus pi etc. at transposition relieves electron and electron density thus stabilizes the system. And the question is PTNC 24 plus plus. So the NaCl is better. So what are the choices? Either this one or this one, right? So if Cl is better, This is the trans. So the choice is either this one or this one. Okay. Is it okay? Others? Okay. So next, let me finish first this. So what are the next factor? The next factor is that as we told, as we know that in most of the cases, let's say you have the steric effect. So how this steric effect? Steric effect of existing ligand. Existing. Let me take the form. So this is the complex. Now you want to replace. You want to replace Cl with H2. Now here the steric effect of the existing ligand. So if that I have to look right first. Pyridine, methyl pyridine, and 2,6 dimethyl pyridine. So this is A72. Oof, every time it is going. So it is, I think all of you have written, so I can, it is 2 into 10 to the power minus 4. I shall write it afterwards. So, so what is happening? So here, another thing I must say that the rate of the reaction, if we just go for order of reaction, then is take takes into account the total concentration of whether it is dependent on the total concentration of this PT, CLL, PT, ET3 and the H2. I mean H2 is the incoming ligand. So the concentration of this one. I mean when we are looking for the concentration of this one and concentration of this one, right? But if we just change the air, I shall, I mean, when I shall upload, I shall give this slides, everything written. So this L also affects, though L do not have any trans effect, so L is not participating in anything, but the approach, right? Even if it is, what is this? That PET2 whole 2. So PET2 and PET2. But here the approach, like if it is pyridine, then you can see this is only in the plane. If it is 2-methyl pyridine, then it is methyl. So the water has to approach. So what is approaching, and these things are not in scale. You can understand when we are thinking of a reaction, this molecule is very small. So this, and then if this is the thing, then these two CH3s is in that way, because this water approach, or from what is happening, I do not know. This water approach is hindered. Approach of the incoming ligand is hindered. Is it clear? I shall go to the next one. Next one, a little bit of understanding is required. Is it clear? Then I shall go. Okay. So the next one is that this one has, if you go through the thermodynamics, this has too many things to understand. But please, at this point of time, just try to understand in a way that could make you understand that what is the mechanism. Like if you have, let's say, X, Y, Z, so this is entropy is high, so they are dissociated. They are, I mean, lying all over the places, so their entropy is high. Now, if you make some arrangement that you just put them in a box, I mean, imaginary, you are putting them in a box, so this is order, and entropy decreases. Do you agree? Do you agree that you write? Then I shall just write the point. Yes, you agree. You have to agree. What can I do? And then if you have a metal complex, let's take a simple complex, NH2O, sorry, H2O whole 4 general. So MCl4 minus. And you brought ammonia. So at this first stage, you have this MCl4 minus and ammonia, and with on the time scale of the reaction, if it happens that they are closely associated, then the entropy of the reaction decreases. And that's tell you that this is going to associative mechanism. So decrease in entropy, that could be measured. That how that can be measured, that is different story. I mean, that we are not discussing. So if the entropy of the this reaction decreases once you add the reactant, and then you can say that this is through associative mechanism. But as you can understand, it has to be detected with very precisely, with very sophisticated instrument, because once the complex formed, again the other Cn minus can diffuse into the system. So again, the volume will increase. So you have to be very precise at your uh, study. Just you have to continuous generally what people do, that continuous monitoring. You have MCL4, you have the volume, they are calculating, and exactly when a drop of NH is given, then it is measured. After some time it is measured with that one drop. So these, in this way, I mean, I'm just trying to explain you how does these reactions are monitored. In that way the reactions are monitored. Okay, and then also the negative volume also same way it is associated. So negative volume means what was the total volume and it is decreasing because of this associative mechanism. Okay, now all these are the discussion. What we did is that we are depending on the concentration and the component of the uh, metal, I mean, the concentration and also the other spectator ligands, spectator ligands, electronic parameter, electronic parameter, as well as steric parameter, we have decided. And if we have first order, and mostly they are second order reaction that we are discussing. Second order means depend on the ligand, depend on the metal concentration. And if you now go for first order reaction, then generally the first order reaction is made to check with this, one of them is constant, and then you do it at the pseudo first order reaction. Okay, so now we can, so is it okay or not? Let me know, and then I shall go a little bit. Hmm. Trans, that I told once, maybe you have missed that. If you make the strength of the ligand, I mean, the trans, if trans, uh, I mean, in connection with the trans effect, if you make any table, then you will have one set as the, in any book you can find, and if you want I can give it to you, but I mean in any book, please read the books. So you will have one uh, one, this greater than for sigma donor ligands, I mean based on the sigma donor property of that particular ligand, and one you will get on the basis of pi acceptor things. And when the actual things, I mean you could see, then you see the combined effect of sigma donor and pi acceptor property, and the whole trans effect series, this series, actually the position of that particular ligand is considered basis based on the, I mean this taking consideration of the sigma donor and pi acceptor ability. Clear? So anybody has any question, because I shall go to the octahedral. So if you please look at this, whatever you whatever I told, and then if you have any problem in understanding, please let me know. I'm waiting, and I can wait for 5 minutes, and then I shall again ask you for the octahedral thing. So is it okay with the square planar complex? So already it's 10:27. So let me just point out only the octahedral. What are the factors that affect the octahedral? And we can explain it on the next day. So please let me know that is it okay about the square planar, or you can read it and you can come back. Okay, somebody can take me. Okay, now the octahedral complex, and it is very clear now that octahedral complex, the number of ligands are quite high, and definitely if there is any associated, it is not that there is no associative reaction, but if there is any associative reaction, then this is a bit difficult and all these things. So what happens? So octahedral, sorry, this. So octahedral complex. So the first one is called. So first it is said that it is not saying. So the handwriting is encounter complex. Encounter complex. If you cannot read it, please read it. Encounter complex. So the first mechanism was given by Eigen. And this mechanism says that before that, let's say there is a reaction, anything, any whole plus, and you have water, and they did not term it as associated on something. They what they say that before they the reaction takes place, they form an encounter complex, which is called. These are the theories. I mean, previously people give, and comma H2. So this is called the encounter complex, and in the same way, this encounter complex gives rise to the reaction NH3 H2O plus NH3. So what is the point? That you have a reaction mixture, this NiNH3 whole 6, and you are adding this water, and this water first diffuses throughout the system. First diffuses throughout the system, and then they come to the vicinity of this uh, NiNH3 whole 6, and then the reaction takes place. And then what they say now the point is that when you are looking for the rate of the reaction, so will you write it in the term of this concentration of encountered complex, or will it write in the term of this NiNH3 whole 2 plus complex? So in this here, what you have to understand that let's say for sake of understanding, you have 10 number of this NiNH3 molecule in the solution. Now, if you add H2O, so will all of them form the associated complex, or let's say 6 of them form NiNH, this whole 6 complex. Now, if you just take this 6 NiNH3, this water complex, then also you are wrong, and then you are wrong in the sense that if instead of 10 you would have 100 this NiNH3 whole 6 complex, then the number of these can maybe not the same order, I mean, for 10, if it is 6, it might happen that for 100, it is more than 60. I mean, it is 80. So it is a little bit confusing. So what will take? So in that case, it is better to take the total of this. Now, if you take for this encounter complex, so we can write one is that KE for that encounter complex. I mean, this is just to tell you that how people have started. I mean, initially. So this K is the concentration of this encountered complex divided by this one on all these things and the Y. And when you have the actual rate of the reaction, then you can write rate of the reaction is K. K is this rate for this reaction, I mean, constant for this. So M total into concentration of Y divided by 1 plus Ke concentration of Y. And as in all the cases, if Ke Y is 1, then you give rate a new constant containing K observed. Actually, what you see is as total and Y. What so if we say that one of the reactions, so how it is complicated? Now what they are telling that if you see the reaction M NaC whole 6 2 plus let's say water, you have NaC whole 5 water plus NaC. Then simply we say if it is second order, we say this is the rate is equal to K observed into K into concentration of this one and concentration of this one. And here also they are coming back to the same point. But what they are telling that no, at some time all of them are not participating in that. And if we can look very well, then we can see there is an encountered complex. So this is one of the theory. And the second theory that is a little bit again. So what they say, in addition to that, this encountered complex characterization that depends on the covalent interactions between the complex and the entering. So this is another theory, and there is a little bit complicated. The thing is there, and I mean, I'm writing it, but is how this K, because if no one knows the K, 4 third pi AQ in A in V by AB T. So here this A is the closest distance between complex and entering group. Na is the Avogadro number and Kb is the rate constant. P is the temperature and V is the Coulombic potential of this system. So this is a little complicated. I'm just telling you this thing. You must know this thing. Now this activation of these octahedral complexes, how does this affect? So the three things. One is the complex itself. There is a leaving group. and there is the entering. So first two case we have thought about the entering group. So what is the relation with the living group? So living group is, let's say, x 23 H2 x is equal to x minus 14. Now, if you have, I'm writing, I'm first writing ln k equal to ln k plus c. Now, this k is so ln k is the activation energy. So you have a activated complex. I mean, this one. So for this activation, this is ln k is equal to standard reaction gives energy. I'm coming. It is easy, not that difficult. So this is called linear P energy relationship or LFPR. Now here, so this is don't. So if you just do it, you will see that I'm just writing it. I shall come to. I'm not write anything. I mean, let's say A, B, C, D. So if you just plot the log k with log of k second in time scale, then you will see that these are the ligand. This is the leaving. So leaving. So they have a relationship. It means that if you go for interchange mechanism, just try to understand this point. Then rate determining step if LFPR, so determines LFPR plot depicts that it is ID mechanism. The rate determining step is ID. If you remember this, that there are two things that one, this is the, so this is the rate determining, where if it is M, So it is M, and here it is the associated formula. I'm writing it here. Okay. So if this is the complex, then depends that in ID mechanism, the leaving group in interchange mechanism, if we do the LFER plot, and then if it depends on the rate depends on the leaving group, then you say that this is ID mechanism. So this is a special case. I mean, for every case there are some other explanation. And then let us go to very simple thing. The spectator ligand. Only two things I shall tell you. So, as you take an example, A9HL5 plus H2O, A9L5, H2O, is X minus. So, if L is equal to NH3 and L is equal to H2O, this is reaction is much faster, right? Because NH3 is better sigma ligand. That here I am not telling about the competing case, because here yes, I mean in some aspect it is competing ligand, because we are taking all of the L are same, and it's the same explanation as the trans effect thing. But in here one geometry also affects, so that we can do with the more examples, that from where it is going and what is the geometry. Like geometry thing we have not considered yet, because in square planar complex one of the main point is that the geometry doesn't change during the transition. And also the steric effect is the same. Steric effect hinders. It is so same in organic square planar, everything. Hinders, or injuring, whatever you like, injuring ligand. And one more point I shall say, and that's it. That ligand field stabilization energy. From here, questions come. That ligand field stabilization energy do affect the rate of a reaction. So what is that? This is called so difference between LFSE of, this is important, of starting complex at transition state or activated state complex. Activated state complex do affect the rate of reaction. And this is called LFAE, ligand field activation energy. So these are the basic points that I told you. I think for octahedral, if you do not understand anything, please let me know. If you want to know right now, this is fine. And if you want to know afterwards, that is also fine. If you have any question, please let me know. The octahedral complexes will do. I mean, if I can finish this, a little bit more is there. This redox reaction, and if we could finish that within Monday, then Tuesday and the next Thursday we'll do more this problems, or we'll do some problems, and I shall give you the assignments on these, and most probably Professor Venkatraman will take the classes after the puja vacation. So in that case, you could submit the assignment. I mean, anytime after the puja, and I can give a little more time because some of them you have the festival, so that we can discuss among ourselves and we shall set the time. But you will have two more assignments, one on spectra, one on this reaction mechanisms, and if you want you can also do the third one. So that is your choice, and I shall request you to I mean, give consent to for another quiz, because we have covered only the bonding part. We have not considered the spectra as well as the reaction mechanism. So when Venkat will take class, we can have just one quiz exam. I mean, you just have to spare 1 hour extra because I cannot take a class from him. So I just you have to give it other than, I mean, Saturday, Sunday, anything, and that you just let me uh, tell me and decide and tell me. It will be better for you. I mean, for that reason, I'm telling. Okay, so you do you have any question? And before I end and the next Thursday, I shall, I mean, appreciate if you give me some feedback about the course content of uh, this course, because as I can understand that you do not know how much of these will help you in the future and all these things, but regarding the syllabus and all these things you have some idea. So because that help, I mean, the last year people have given me just for not formal, just informal, in chat box or in WhatsApp or in mail. So in that case, it is better for us to design or include or exclude the portion that is you feel, I mean, we can I mean, include your views also in the course content, right? I think you do not have any more questions, so thank you.